Hello, everyone. Namaste, good morning, good afternoon, and good evening. Well, it's late evening here in Nepal. It's GMT plus 5:45, and we are here back again with brand new episode of a webinar on geoscience for sustainable development. This is Suraj Gautam, a civil engineer and a DRRM professional from Institute of Himalayan Risk Reduction. First of all, I would like to welcome you all in our Himalayan webinar series. Institute of Himalayan Risk Reduction is an organization established with a vision to prepare risk-informed societies for disaster resilience and sustainable development. So, to contribute onto this, IHRR has been regularly organizing a Himalayan webinar series on geoscience for sustainable development and disaster risk reduction and management. So far, we have successfully organized 10 episodes of webinar on geoscience for sustainable development. And yes, today it's the turn for the 11th one. And today we'll be having an interesting topic on debris flow dynamics and obstacle interactions through multiphase models, which will be presented by Dr. Parameshwari Kattel. And on behalf of the organizing team, we are really grateful to our presenter who will be sharing us with his insight and healthy experiences. So it is indeed an honor to welcome our presenter for today, Dr. Parameshwari Kattel, who is Associate Professor at Department of Mathematics, Tri-Chandra Multiple Campus, Tribhuvan University, Nepal. And to make this session interactive and more lively, we have Assistant Professor Dr. Basanta Adhikari from Institute of Engineering, Tribhuvan University, as our session moderator. Dr. Adhikari is also the visiting scientist at IHRR. So we'd like to welcome you. We'd like to welcome you all, and especially to all of our participants who are joining us through our social media, live streaming, and also through this Zoom platform. This webinar event has been featured in the website of Relief Wave. And talking about the webinar registration, till date, we have more than 147 registrations from different parts of the globe. And to address this request, we are going live on our social media page of Institute of Himalayan Risk Reduction. So you can also follow our live streaming. And we'll be receiving the queries and feedback from our social media and as well as from our Zoom chat box. We have been organizing webinar series on geoscience for sustainable development on a regular basis. And we believe this webinar series has been supporting our early career scientists, DRR professionals, academicians, and all the participants. And yes, it's a beginning. We will be having a long way ahead. And so before starting our session for today, I would like to share some brief introduction about Institute of Himalayan Risk Reduction. Institute of Himalayan Risk Reduction is an organization established with an objective to assess the risks and understand the risks to contribute for the sustainability. Our team constitutes of expertise, professionals with expertise and experiences in the field of DRR in understanding the risks, conducting academic research and field level implementations in Nepal and across the globe. And we have a vision of preparing risk-informed societies for disaster resilience and sustainable development, and a mission to prioritize, train, and mobilize DRR professionals and promote the solutions through science, engineering, technology, and innovations. So we have four thematic areas that includes disaster risk reduction and management consulting. Another is research and development. The third one is the disaster academy, and the last one is youth in disaster risk reduction and management. And so far, we have accomplished a number of projects that includes the transboundary hazard projects, where we studied the landslide risk assessment on the Sino-Nepal road corridors. We have also collaborated with the number of local governments to bring out the UAV surveying. And also, during this COVID-19 response, under the collaborative approach, we collaborated with a number of organizations and developed a national platform for the information dissemination, which was later endorsed by the Ministry of Health and Populations. Besides, we have been carrying out this UAV surveying in Hetauda sub-metropolitan city. uh, and we have also published our voluntary commitments in the Sendai, as you can also see over here. And this is what we have been doing under a regular interval Himalayan webinar series. And we are also happy to announce that we are organizing this virtual conference on disaster risk reduction on 19 to 21 March 2021. So it is jointly organized by the National Institute of Technology, Karnataka, Surathkal, Asian Disaster Reduction and Response Network, and Institute of Himalayan Risk Reduction. So we have Springer as our publication partner, and the details about this conference can be viewed from this website. You can go through this. It is also seen in our website. And so today, now we'd like to move on to our regular session. That is, we'll be having a presentation now. And I would like to share some house rules for this webinar. The audio and video of the participants will be switched off. The overall session of this webinar will be recorded and will later be provided in the YouTube channel. And for any queries, the participants can write off in the chat box or in the comment section of the Facebook streaming live. And the waiting room has been enabled, and only registered users with their original identity will be allowed to enter the webinar room. So I would also like to request our participants to post their questions. And yes, the feedback links will be provided during the session, and we'll be providing the participation certificate to our attendees. So without any further delay, I would now like to move on to our session, and may I request Dr. Basanta Adhikari to proceed further with his moderation. Thank you for now.
Thank you, Suraj. Am I audible and
yes,
visible?
you are audible and visible.
Wonderfully start. Executive Director, Suraj Gautam, Institute of Himalayan Risk Reduction. Welcome everybody. And I'm very pleased to moderate this session of tonight with my esteemed guest, Dr. Parameshwari Kattel, who is well-known applied, I would say that applied mathematician in Nepal, and most of the young generations, they are really following his path. And so he's basically working on this, how applied mathematics can be used in physical modeling, especially in different terrain and different rheology and different geomorphological setup. For example, in the Himalayas, glacial lake outburst plot, debris flow, and so many things. And he is my good colleague, and we have known each other for more than 5 years. And I always admired his dedication in this field, and I always follow his publications in this applied mathematics field. So Dr. Kattel, he is an associate professor at Department of Mathematics, Tri-Chandra Multiple Campus, Tribhuvan University. He completed his PhD in Applied and Computational Mathematics from School of Science, Kathmandu University. Currently, he is an associate professor, as I already explained about his CV, and his research interest mostly focus on mathematical modeling of multiphase mass flow and obstacle interaction, which is really applied field in the Himalayas, in this terrain. And he's also involved in different projects, but mostly which are really important. And I was very pleased to interact on this project, which is one is Swiss University Development and Cooperation Network, Consortia for Education and Research, and second cluster of cooperation in Global South. And he's, as I explained to you already, he's well-known scientist, so he has delivered scientific talk in many international and national conferences related to mathematics and geophysics and geodynamics. He's an advisor of Council for Mathematics Education, the Gandaki province of Nepal. And he's also served as the president of Council of Mathematics Education, Kaski, from 2000 to 2013, which is really 2010 to 2013, which is a really good time. And Joint Secretary of Nepal Mathematical Society, 2015 to 2018. And when I knew his research on this field, and we have invited him to give a talk about how can we implement the mathematical modeling, or what we call the numerical modeling in the this geodynamics and physical geology or geography, whatever you called. And then he accepted, and I'm very pleased to invite him, Dr. Kattel, to deliver his talk on debris flow dynamics and obstacle interaction through the multiphase models. So, Dr. Kattel, please proceed. The floor is yours.
Thank you, Dr. Basanta Adhikari, for the nice introduction. I'm sharing my screen. In the meantime, I'd like to congratulate Suraj Gautam for the recent research opportunity that he grabbed from Kathmandu Metropolis. I read this somewhere in the news. Is my screen seen now?
Yes, we can. Yeah, it's visible now.
Thank you very much for the nice introduction. I'm not young, but I'm scientifically young because I'm working in the research area since my PhD research work. And in this talk, I briefly outline the works that I carried out during my PhD that have already been published, and some are being published. They are in revision phase, and some have been submitted. Then, as a presentation plan, then I briefly discuss the employed model. Then a very brief introduction about the numerical method we employed, and then debris flow akin to glacial lake outburst floods, and interaction with the interaction of debris flows with tetrahedral obstacles, and later with the converging shear walls. And finally, I will discuss about the newly developed multiphase debris flow model, in which the multiphase virtual mass emerges during the model development. So the slope failure occurs when the destabilizing force overcomes the resisting force. And then, but we do not, I do not focus much on the triggering factor. Our main focus will be on the dynamics and the obstacle interaction. And debris flow, as to introduce in brief, it is a water saturated landslide due to the rapid motion, the high momentum and kinetic energy, and mainly the interaction of the solid and fluid forces, and make the debris flow more devastating and more dangerous than the dry landslide and the flood. But the dynamics of debris flow can be affected by mounting the obstacles on their way. They can alter the path, and they can redirect, or they can arrest the mass, and that make the debris flow less hazardous. So anyway, the proper understanding of dynamics and flow obstacle interaction is required for constructing the appropriate defense structure, and especially for the risk reduction. So installing of the defense structure is one important aspect of active mitigation measures. And the defense measures that may include single or multiple units of structures. So as for example, we have in the left figure here, we have your avalanche, your mounts, and then that followed by the catching dam. And the second one in the middle is the avalanche defense structure that I witnessed in Galtur, Austria during my research stay out there. And the third one in the right is the shear walls in the Ilgraben debris flow in Switzerland, where in this region 6 geophones were incorporated to measure the impact force. But we compute the impact force through the simulation results. And protection measures can be of diverting or retaining, or the drainage type, or passing through type. But in many computational experiments, I have chosen the pyramidal defense structure. In fact, they are efficient and elegant to look at, and they are also efficient in diverting and restraining the debris flow mass. And in a couple of numerical experiments, I have chosen the lateral shear walls as embankments, and they can be useful to mitigate from the destructive potential by scouring. So let me introduce briefly about the model. This is the full dimensional model. The previous two are the mass balance equations for the solid, the first one for the fluid, and the last two, these are the momentum balance equations for the solid and the fluid. So here some physics are proposed by Puraseni 2012, where the interfacial momentum transfer, MS and MF are given, and that mainly involve the drag force, the first term, and the virtual mass force, the second term. The solid stress, we have more Coulomb plasticity for the solid, and the fluid is modeled by the Newtonian viscosity, and the next one is the non-Newtonian viscosity. This is the new aspect of the model, as because of the solid matrix in the front, the fluid viscosity sometimes is enhanced and sometimes that is downplayed. And such non-Newtonian viscosity due to the gradient of solid volume fraction has also been incorporated in this model. But this model is full dimensional. And for the computation, this is not that much useful because it demands high computational cost. So some scaling is done and depth averaging and some appropriate boundary conditions. Then there is the depth integrated model where the jet direction has been averaged and that is represented by the flow depth. So the first one, these two equations in the box, they are the mass balance equation or conservation of mass. The first one is for the solid, and the second one is for the fluid. And we have the four momentum balance equations. The first one is for solid in x direction, that means the downslope direction. The second one is for the fluid, that is for the solid in y direction, that is cross slope direction. And the third one is for solid, the fluid in x direction, and the last one is for the fluid in y direction. So we can see that in the inertial terms, this script C, mathcal C, which represents the virtual mass coefficient. So this is important because in the last model also we have some focus on it. So to briefly introduce it, sometimes what happens, as a debris flow is a two-phase flow, and during the flow, when solid accelerates downslope or cross slope, at that time the ambient fluid surrounded in the solid, that is also accelerated. That is solid gains inertia due to the ambient fluid. So at that time, the virtual mass force or the added mass force is evolved. So that is incorporated through the virtual mass coefficient in the inertial terms. The right-hand side are the complicated source terms, which are given in the next slide. The first one is the source term for solid in x direction. It contains gravity, Coulomb, topographic pressure, buoyancy, and generalized drag. And the fluid, so the fluid forces are more complicated than the solid. That also contain the gravity, fluid pressure, topographic pressure, and viscous stress. It is Newtonian. The first part is Newtonian, associated with this quasi-Reynolds number NR. And the second term associated with this mobility Reynolds number, that is the enhanced viscous stress. That is the non-Newtonian viscous stress. The generalized drag incorporates both the solid-like and fluid-like drag. It incorporates more physics like the terminal velocity of the freely falling particle, and the solid and fluid-like drag, they are interpolated by the interpolation parameter P, and gamma is the density ratio for fluid to solid, and these are all other parameters. And we numerically integrate them by using high resolution shock capturing numerical scheme, namely TVD NOC, that is total variation diminishing non-oscillatory central. Then we have the material parameters and basal topography and the appropriate initial and boundary conditions as input. And as output, we have the debris flow depth and solid volume fraction and the velocity components for solid and fluid, both in the downslope and the cross slope direction. So as the gravitational mass flows like debris flows and other gravitational mass flows, so we can see the large deformation, rapid motion, and some obstacles interactions on the way. So these TVD NOC method, that is effective even when the shock is produced during the motion. So this is the staggered grid where we computed, numerically integrated the field variables. So the field variables are averaged in this half time step. We take the average from these cells, and then we compute the cell center as the full average, and then and in that way we go on proceeding. So in that due course, the staggered grid is formed. So I will not discuss more detail on this. So anyway, in the gravitational motion, in the real field event, it is very difficult to take the field data during the event because it is hazardous. And moreover, the lab experiments cannot replicate the real events in effective way, because we cannot replicate the use appropriate boundary condition and the field scenario in laboratory. And there is another difficulty of upscaling. So in that case, numerical experiments or simulations are the best and the promising options, where we can give all the essential parameters or the physical parameters, and we can choose the effective models and effective numerical tools and carry on the numerical integration. So as now I'm going to present some of the results that was published in Annals of Glaciology, entitled Simulating Glacial Lake Outburst Floods with a two-phase mass flow model. So here, as simulation setup, we have three different type of geometric setup of the glacial lakes and the boundary conditions. For example, here we have one simple sketch of the glacial lake, where it is dammed by some moraine here, side moraine and the frontal moraine. Sometimes if the all around they collapse, if the side moraine are very thin and the frontal moraine is thick, it can be modeled as in the first figure, where we have this thick frontal solid rich frontal moraine that holds the glacial lake downward, and it is in the form of triangular ways. The lake structure is taken in the triangular ways. Although the first figure is not that much realistic, because there should be some mass holding the lake from the lateral side also. This is just for the mathematical experiment, what happens when this type of flow is triggered. In the second one, the lake is also held by the lateral conduit walls, and the wall also continues some distance downstream. In the third scenario, the lake volume is increased by is laterally widening, like fan type glacial lake. And then what type of scenario will be developed in our numerical experiments? So in this, these are the parameters chosen: the internal friction angle, the basal friction angle, the terminal velocity, the particle Reynolds number, like that. Then interpolation parameter has been chosen to be 0.5. The inclination, the slope is 45 degree we have chosen. Density for solid is 2,800 kg per cubic meter, and that for viscous fluid is 1,100 kg per cubic meter. So the lake has this structure. So from 0 meter to 25 meter, there is fluid lake which contains 95% viscous fluid and 5% solid material. And the moraine dam is 80% is solid and 20% is fluid. And it extends from 20 meter to 25 meter. And for the first time in the two-phase debris flow dynamics, we have incorporated a nominal bulk drag in the source terms of the solid and the fluid momentum equations. Later on, some researchers also begin to consider this ambient drag so as to address some drag due to the air resistance or something like that. Citing our paper, many researchers have started utilizing this. So in the first scenario, the first geometrical figure is that the frontal moraine dam is there, but we don't have the side moraine there in this figure. And then in this simulation and the simulations that follow, these first left panels are for solid dynamics, time evolution of solid phase. And this is the time evolution for the fluid phase. And the last one is for the debris bulk as a whole. The last one is the aggregate of these two, the solid and the fluid. So when the glacial lake is triggered, at the time the solid and the fluid phase both advect downslope, and that advex that disperse cross slope also. Now they begin downslope, they begin to advect downslope. They, as time elapses, they advect downslope and they also disperse in the crosswise direction. So this is the overall the dynamics we have shown. So I request you to see at this time slice 5 seconds. This is for the solid, this is for the fluid. Fluid is in the middle and the solid is in the front. So to aggregate this, this is the total flow scenario where the frontal levy is due to the mechanically strong solid, and the back portion of the debris body is due to the fluid, as we can see these two figures. Such scenario we also observed in the SETI debris flood of May 5, 2012. This is the snapshot of some debris flow source or the mud flow source or the SETI flood source. So this is the snapshot. So where we can see the frontal levy, and then that followed by the fluid-rich debris body. So in the second setting where we have the conduit walls also, is more to make it more closer to reality, we have taken this scenario. And due to the boundary condition, then the fluid dynamics is completely different. So we can see these lines these small lines, thin lines are the conduit gate exits. And when the flow exits the conduit gate, firstly they were pressurized and directed in the downslope direction, but later on they begin to disperse in the y direction also. So in this way, the debris plume is developed, and then that moves downslope, and the flow geometry is completely different from the previous one. In the third simulation scenario, we have increased lake volume. So because of that different lake volume and lake geometry, the lake emptying process is different. It takes longer time to empty the lake, and so there is the longer tail of fluid. And then on comparing from the first to this second figure, then the flow little bit advects downslope because of the high pressure due to the lake. Now, let me discuss some results that was published in the journal Engineering Geology. That is the interaction of two-phase debris flow with obstacles. And mainly we have chosen the pyramidal or the tetrahedral defense structures. And these are the equations of the sides of the tetrahedron, which I don't want to explain. Anyway, with this geometrical domain, we can take this. And why we are taking this two-phase model to discuss the debris flow interactions, why two-phase model are different. So if I could show you one small video clip, then that may be useful, but it is taking a bit longer time to open this. Okay, hope it will open soon. So in this, so I don't know why it is taking a bit more time.
It's come, it will open, wait.
Okay. So here of two-phase debris flow is triggered, then the flow that moves from the upstream direction. The debris flow is a bit woody type, not stony type, but it looks a bit woody type. Now there is a boulder as an obstacle in the side. Now in the due course of interaction, the solid phase is obstructed due to the obstacle. And some part of the fluid and the solid that moves downslope, but some part is arrested by the solid mass there. So let me close it. So I think you have noticed this. So we just saw here that the solid and fluid in the debris flow did not only show the dynamic difference in the dynamics, but they also show different obstacle interactions. Solid and fluid, they are possessing different obstacle interactions. So this shows the need of the two-phase and if possible multi-phase mass flow models to simulate such kind of flow. The first figure is the undisturbed flow as the reference simulation. There is no obstacle on the way. So it is a free surface flow. So when the solid phase and the fluid phase both, they advect downslope and then they disperse cross slope also. So as time elapses, solid and fluid, they are showing some different in dynamics. We can see clear dynamical differences between solid and fluid. So here at around 9 to 10 seconds, the solid, as we have the uh, slope at the first, and that is followed by the horizontal runout. And because when the gravity force is seized and the solid and fluid, they both begin to show the deposition morphology. So the simulation is stopped at time 10 seconds. Now we mount an obstacle on the way, or pyramidal defense structure, forward facing. That means when the debris flow is triggered at time 2 seconds, the solid fluid and the total debris bulk, they all meet the frontal nodes of the pyramid. And then when they interact at, we can see at time 4 seconds, the third panel downward, they are deflected due to the obstacles. And the deflection continues as time progresses. But here, from time 8 seconds onward, the solid and fluid, they are showing different obstacle interactions. And you can see the color maps in the right-hand side of each panel, which shows the phase depths. This is the solid phase depth, and this is the fluid phase depths. Then we can see the solid maximum is near in the vicinity of the around the obstacle, but the fluid are easily passing through the obstacles. As time progresses, the fluid moves more downslope. That means solid are obstructed by the obstacle more rather than the fluid. And such kind of different dynamical and obstacle interactions cannot be shown by the single phase model. So this shows the importance of the multi-phase or two-phase models. So that two-phase models we are implementing. Now in the second figure, we changed the orientation of the obstacle. Previously, the frontal nose was interacting, but we have given a half turn to the obstacle. Now the blunt face will interact. So we can see the different dynamical interaction with the obstacles. Now we can see at time 9 seconds, here 9 seconds onward, so more solid is obstructed than the fluid. In 10 seconds, a substantial amount of solid is arrested by the obstacle, but a very small amount of solid, a part of inside the solid matrix is obstructed by the obstacle. So such kind of difference in dynamic and obstacle interaction can be seen while changing the orientation of the obstacle. So we also computed the impact pressure. So in the first case, we at time 4 seconds, there is the maximum interaction with the obstacles. So we computed the, first of all, taking the solid phase depth, fluid phase depth, and their separate velocities. We computed the mixture density, mixture velocity, and the total debris depth, and we computed the dynamical impact pressure. And later, we also computed the solid phase pressure separately and fluid phase pressure separately. And so we computed the barycentric impact pressure computed from the both phases. And these two are different. The first one is around 112 kilopascal, but the second one is 124 kilopascal. Then we can see that the dynamic impact pressure computed from the phases or the mixture and the barycentric impact pressure computed from the phases, they are different. That may count a lot in the hazard mitigation strategy or the active mitigation strategy for the risk reduction. So we think that the barycentric impact pressure is more legitimate to use. Then that is my question also. What do you think, the engineering people and other scientists, what do you think? We just think the barycentric impact pressure is more legitimate to use, the noble barycentric impact pressure. So then we mounted the obstacles, 2 more obstacles in downstream, where the obstacles are smaller in size because they are to interact with the halfly divided the debris lobes or the debris streams. So I didn't show the interaction before 6 seconds because that is similar to the previous ones. So at time t second, the 2 lobes begin to interact with the 2 more downstreams downwards. As time progresses, multiple debris lobes can be seen. The first one is for the solid, and the second one is for the fluid, and the last one is for the total debris ball. Here, from time 12 second and 13 second, we can see that more solid is deflected outward and more fluid is deflected inward. So such interesting dynamical feature has been seen in numerical experiments, but these we have already been seeing in natural events, because after the interaction, we can see in the flood also. So when it interacts, when the slope changes from rapid to gentle, or it interacts with some obstacles on the way, so the more solid is thrown at the outer banks and more fluid will be flow in the main path. And it has some applications also, because those solid can be used as the constructing material like the gravel, sand and boulders, and the fluid can be used as the hydroelectric feed and irrigation. So anyway, the risk can be reduced in the debris vacuum where there is no flow region. So we named it debris vacuum. So in that region, the risk can be reduced very well. So we just slightly change the orientation of the obstacle. Here, the downstream obstacles are also backward facing. So at that time, we have seen a little bit of dynamically different obstacle interactions here. Here, solid is abstracted outward and the fluid is abstracted inward, and a little bit of fluid is only deflected outward. So here, we made the 2 downstream pyramids in such a way that the flow is directed towards inward direction. Here we can see that we do not see the multiple lobes. However, the fluid and solid both are directed inward. So the outer bag, in the outer side, the risk can be reduced in this geometric constellation of the obstacles. Here we can see some in time 13 seconds in the solid panel, some solid has been arrested by the obstacle, but the fluid is not arrested by the obstacle. In next figure, the straight, that is the downstream pyramids are kept straight, and we have little bit of different dynamical interaction with the obstacles, and we have seen the more pronounced phase separation here. In the next one, the flows are directed outward. So you can see the arrangement of the downstream pyramids, these 2 downstream pyramids, and the flow is directed outwards. Both solid and fluid, they are directed outwards. And the advantage of this is that if some settlements are there in the middle region, then the settlements or any infrastructure in between them can be saved from the debris flow by redirecting the debris flow outward. So next, we take the lateral converging shear walls. So we have taken these lateral converging shear walls in outer region. So this is the slit width. We can vary this slit width, means we can make this opening sometimes wider and sometimes narrower. So in the first figure, the slit opening has only the width of 2 meters. At the time, the solid and fluid both are momentarily obstructed, and what we can see the dosing of the flow. Here we can see the more solid phase is obstructed here between the lateral shear walls, converging lateral shear walls, but less fluid has been obstructed here. In the next figure, when the slit width is made open, you can compare these two. We have changed the, yes, you can also compare. I will just go in the previous and the backward slide. You can see the difference of the dynamics and the obstacle interaction. In the last figure, when there is wider opening, what happens? the solid and the fluid, they are less obstructed than the previous figure. Still a little bit of solid is obstructed, but the fluid that already passes through. And then because of there is a wider opening, that runout distance has been increased by a little bit, but it should be increased by more, but it looks a bit counterintuitive. But we see that in this case also, because of the pressurized flow, the runout distance has been also increased in the previous when there is the narrower slit opening. So by varying this slit opening, then we computed, mainly you can see in this 5-second time, there is the maximum interaction with the lateral converging shear walls. So we computed in the 5th second. This is with no obstacle. This is the reference simulation with no obstacle. This is the flow geometry of the solid. We are just discussing the solid and obstacle interaction. So from this part, the debris flow begin to interact the shear walls. So this width is denoted by capital B, and this opening of the slit width is by small b, and contraction ratio is KB by this formula. So when there is the 32 meter of opening, there is 16 meter of opening, there is 8 meter of opening, and there is 2 meter of opening. In this 4 scenario, we have computed the contraction ratio, and obstruction is there. By here, we can see the 4 meter. Here, we have seen more than 5 meter. The debris depth is here more than 6 meter. What does that mean is that more solid is obstructed here in between the shear walls. So we computed the obstructed percentage by that formula. And we also tried to see the relation between the obstruction and the contraction ratio. And the obstruction increases along with the contraction ratio, and it increases more rapidly for the higher contraction ratio. That means the narrower width opening. And then in the next phase, as the mathematics student, we have to develop some model. So we worked on the multiphase model. So we were working, we worked on the 2-phase models, and then we performed some numerical experiments, and we did some validation with some results also, mainly in the fluid numbers, which I didn't show here. But anyway, we were excited then. Sometimes it is more realistic to treat a debris flow as a 3-phase model. Sometimes the coarse sediments, like big boulders and cobbles, gravels, and sometimes there are fine sediments like sand and other fine particles, and the viscous fluid. They have some different rheology. For example, the more Coulomb plasticity can be used for coarse solid, and for the fine solid we can use some Coulomb plasticity, and for Newtonian or non-Newtonian viscosity for the fine solid. So why not to treat a debris flow as a 3-phase model? So we were motivated by this, and we treated debris flow by these 3. And we mainly took into account the virtual mass force. Actually, virtual mass flow is very important mechanical aspects of mixed mass flow. Then we cannot ignore when there is rapid motion, and when there is the velocity difference, drag inverse. When there is the difference in acceleration between the phases, then there may evolve or emerge the virtual mass forces. And then virtual mass forces are still poorly understood, and sometimes they are ignored, and in some cases they are included empirically. And so they are useful to more accurately predict the flow variables, including the velocity fields and pressure. And virtual mass forces, including virtual mass forces in the model, that not only gives the accurate prediction of the field variables, that also increases the computational efficiency of the model. So here we have treated debris flow as the 3-phase: solid, fluid, and fine solid. But fluid can be entrapped in fine solid because there are interstitial spaces between fine solid, and there are interstitial spaces between solid. And in natural reservoirs, the solids might have some natural fractures where petroleum or groundwater can be entrapped. Similarly, fine solid can also interact in the solid. So we have, although there are 3 phases, but there are 6 fields now. What are the 6 fields? Solid, fluid, and fine solid. Fluid is divided into 3 parts: bulk fluid, and fluid entrapped in solid, and fluid entrapped in fine solid. Similarly, fine solid is also divided into 2 parts: bulk fine solid and fine solid entrapped in solid. So we have the hold-up relation. This is the solid volume fraction. This is the bulk fine solid. This is the fine solid entrapped in solid. And the next 3 terms, the bulk fluid, the fluid entrapped in solid, and the fluid entrapped in fine solid. And that the total volume fraction is 1. Now we also related the phase fluxes of the bulk and the entrapped fluxes. So, and we have also estimated the velocity. We assumed, and it is realistic or legitimate to assume also, the fluid entrapped in solid also moves with the velocity of the solid. And similarly, fine solid entrapped in solid, that also moves with the velocity of the solid. So entrapped, this volume fraction of the fine solid entrapped in solid, that is a certain fraction of the volume fraction of the solid. Similarly, we related. So we wrote the equation of the mass balance equation of all those 6 fields that I described, and the momentum balance equation. This is the solid momentum equation. This is for solid, fine solid entrapped in solid, and fluid entrapped in solid. For fine solid momentum equation for fine solid, and the momentum equation for fluid entrapped in fine solid. So here we have the pressure term, gravity term, these are the drag terms, and this is the viscous rheology. And we have considered the drag and viscous rheology as a generic one. According to the flow situation, we can use any type of viscous rheology here. The advantage of the model is that these terms are generic and we can use the appropriate type. And this is also the fluid momentum equation. So we added them and we proceeded with a long, rigorous mathematical procedure, pages and pages of simplification. We arrived, so I don't want to discuss these steps. So we finally, previously, we don't have the virtual mass forces in the model. But when we considered the entrapments, when we divided the phases into the fields which are entrapped, the fluid type material entrapped in solid type material, then we arrived in the momentum equation for different 3 phases with virtual mass forces. Previously, there were no virtual mass forces, but due to the entrapments, look, these terms in color magenta, they are the virtual mass forces. This is the relative acceleration between the phases. And then this is the virtual mass force for the solid, between the fluid and solid here, between the fine solid and solid, because this is the momentum equation for the coarse solid. So solid, that means coarse solid, that is with fine solid and with fluid both. So we can see that the drag forces, they are also improved, and the viscous forces, and previously we have the simple viscous force, but the viscous forces has been substantially changed by this quantity. We can see in down here, BFS. And the feature is that the entrapment induced inertial changes are taken account by the virtual mass force terms. Previously, the fluid is entrapped in solid, fine solid is also entrapped in solid, and these entrapments were accounted by these virtual mass forces. This is the noble contribution of the model is that. Similarly, we have the momentum equation for the virtual mass for the fluid, and this in color magenta. Similarly, we have for fine solid and then fluid. So we have completely different momentum equation for solid, fluid, and fine solid. But these models are yet to be depth integrated and they are subjected to simulation. And yes, I want to repeat that the important aspects of the model is that we have the induced enhanced viscosities of phase fraction, viscous stresses for coarse solid and fine solid. And these are the noble aspects. And the viscous rheology and the drag, they are the generic, and we can use any type of viscous rheology out there. So it can cover the whole spectrum of the mixture rheology from the dry to wet of each phase limit. So, and our model has been well reduced in the existing two-phase models. For example, that of Cook and Harlow for bubbles and fluid, and then the model of Puraseni 2012. And we also reduced the model. So this is our new model, the reduced virtual mass forces. So we compared with the previous existing two fluid models, and we performed some simulations out there. So when we took two different entrapment coefficient, fluid entrapped in solid, we have taken 0.2 here more so fluid is entrapped, here less fluid is entrapped. So as there is less coupling, then you can see very clearly that the solid and fluid, they move more independently. Almost all solid is deflected outward and almost all fluid is deflected inward. That is the dynamical difference between this consideration of the virtual mass force. But what is the entrapment coefficient? What is the appropriate value of the entrapment coefficient? This depends upon the morphology of the place where what is the interstitial spaces between them. So for that, just we put some numerical value. So for that, we have to sit together with, for example, like Dr. Basanta Adhikari, the geomorphologist, and we are the engineer and geologist, and to decide what are the important. So the work done by us, that is not complete enough. So your help is needed. So I want to briefly describe, Dr. Adhikari, I have some minutes left, or I have to move?
Yeah, please conclude within 5 minutes.
Okay. So this is another result, Kattel et al. That has been, I'm also a co-author, that is published in Acta Mechanica. Here, the different type of obstacle is taken, bump or circular bump as an obstacle is taken. This is the geometrical setting of the reservoir. So we have discussed here the flow structure interaction, not only with the reservoir, but also with the obstacle mounted there. There are different constellation of obstacles, but just I presented only one result, taking the permission of Dr. Kattel. So as this scenario, we have the Lake 464. So I just have seen this figure in one article of Brikuti Rai, Lake 464 and Mount Chamling at the sea has indicated some possible avalanche, and that may impinge on the lake. So this lake is also laterally expanding, that somehow resembles with the reservoir that we consider the third type of lake we have considered. And when the mass that impinge on the obstacle at that time, the waves will be generated, waves or small scale tsunami, what we can see. And the tsunami will propagate downslope and across both. Then previously the lake had this reservoir has only the height of 25 meters, but we can see it has increased to 40 meters because of the waves, water waves, and the waves are localized towards the side of the reservoir, and they also propagate, and this increase the risk due to the mass flow, and also together with the waves also. So such kind of waves can be reduced by the obstacle interaction. So if we mount some obstacles here, at the time the obstacle reduce the impact, and then the wave has the less intensity also. That has been in detail shown in that paper. So in another way, we have taken the mixer mass flow, Khatri and Puraseni 2018, and some simulation has been carried by taking there. Previously, we have the downslope and cross-slope direction, but we ignored the cross-slope direction, and instead of that, we have taken the jet direction also. Now we can see when this is the wet avalanche taken in a box, wet snow taken in a box. When it is triggered, when it is open, it interacts with this wall, and the wall stops the flow. You can see the geometrical evolution. And when it overtops the wall, then it makes an airborne jet. It detaches from its main body and it lands back on the slope again. And then it again advanced downslope. So although it has been carried in small numerical setting, it can be extended to the larger numerical setting for this jet direction also. So to summarize, solid and fluid phases in our numerical experiments, they have shown very much different flow dynamics and obstacle interaction, and barycentric impact pressure from the phases, and they are still to be validated, and that shows existing newly developed multiphase models are efficient to describe the mass flows in generic topography, and some successful modelings are there in also real field topography, but it needs more multidisciplinary settings with engineers and geologists for more real field applications. So my request is that can we work together maybe with you people or with your students? We can employ your students, and from some mathematical, we have some group, and some mathematical aspects we can guide them, and then the physics and this engineering aspects you can guide them, and then we can work together. That is my appeal. So these are some references that I have cited. So I acknowledge Professor Dr. Shiva Purasaini, Bhadraman Tuladar, my supervisors, and University Grants Commission for financial help in my PhD research. And then with my colleagues, Dr. Jeevan Kafle, Kim Khatri, and Pushkar Pokhel, with whom I shared my lot of experience and ups and downs during the research. And yes, I also am acknowledged with Dr. Basanta Adhikari. I've shared so many ideas with you during those 5 periods of time. And yes, for Suraj Gautam for providing the platform, and all the IHRR family. And then this is my contact. So thank you very much for your kind attention. So I love to welcome to listen to your queries, comments, discussion, and if there is some possible collaborations to carry on. Thank you very much.
Thank you, Dr. Kattel, for your impressive presentation. And I'm pretty much sure that is sometimes it is difficult to explain these equations inside, and the pages and pages equations, and sometimes it is really difficult for us to understand everything. But what is important at the end is that how can we implement such kind of models for the mass movements in the Himalayas. For example, the snow and debris that occurred in Langtang Valley in 2015 Gorkha earthquake, and 2014 the Jure landslide, and then maybe when you talk about this earthquake generated landslide, if you talk in 2005 Kashmir earthquake, or 2015 Gorkha earthquake, and so on and on. And these to 2020 monsoon in the Himalayas is really widely opened our eyes for implementing your models. And yeah, I have a couple of observations during your presentation. I request our participant to post your questions. If you have, Dr. Kattel, can you close your screen sharing?
Yes, okay.
Yeah, wonderful. So, when I talk about these multiphase models for, mass wasting modeling, or what you call the debris flow or something like that. And quite impressive, based in Nepal, what you guys are doing with you and your supervisor, your groups, to whom I know for a long time. And it's really impressive. And thanks for summarizing beautifully your work today. So I will take some of the questions that our friend and colleagues have already posted. So I'll take one question first from Facebook, from Upendra Baral. So he's writing that what is the accuracy of the model you describe, and if it can measure the thickness, for example, subsurface thickness, then what is the depth and what parameters does the model needs? This model is really applicable in Nepal, where we are facing numerous mass movement in Nepal. So basically, this is quite really important. But how can you measure the the thickness of the material, what we call subsurface material, like debris flow or in moraine or whatever? How do you integrate this parameter in your model? Can you explain a little bit?
So in the model, Thank you for the nice question. So as you talk about the accuracy of the model, so we have not made the proper validation with some field or the lab experiments, but we believe that the it is based on the physics. It's a physical mathematical model. So as far as the good physics are incorporated here, and the efficient numerical techniques have been incorporated, then we believe that it should be accurate in more degree, but actually it needs some more field validation. And there are some field validation. Margili et al. Have carried on some validation in the Cardia Blanca, Peru, and somewhere in some back analysis has been done also. Yeah, they have found, according to the back analysis, they have found 71 or something like that percentage of accuracy by the model, because the data are not so much validated, because they are mainly based on the deposits made out there. So, so in our model, then the main output is the debris flow depth H and the volume fractions of the solid and fluid. So at any space, at any moment or time and space, so we can have the outputs as the solid phase depth, fluid phase depth, and their velocities. So in our generic topography, so at any instant of time, at any space in x and y direction, or at any x and y point, we have these outputs, the velocities for solid and fluid in the x and y directions, and we have the material depth. So I also showed some material depth, debris flow depth H, as indicated by the color maps in the slides. So because of that, we can compute everything. So this material depth, these velocities, they can be employed to calculate the momentum, the kinetic energy, and the impact pressure.
Thank you, Dr. Kattel. Yes, what Dr. Boral was asking is quite, really important, because Dr. Boral is very nice geologist in the Himalaya. So yeah, that's why we're always talking about physical modeling and then the numerical modeling and then mix up, so that we can take the data from the field to validate your numerical model, or what you do the numerical model and then you validate that in the field. And that is the two interaction that where the mathematical scientists from the mathematics background and the scientists from geoscience or engineering background can work together. So another question from Akash Acharya. I suppose he is engineering geologist. So wonderful research, hats up, sir. So his question is, do this relation valid on transportation zone, for example, high velocity region and steep channel when the sediments are transporting, or only in the depositional zone where very low velocity and wide channel? So can you apply your model both in transportation zone and deposition zone, or only in the deposition zone? That's the main question.
As I have also shown, then we have taken the track and the runout zone both. So as the flow is triggered, then it moves rapidly downslope. Then when there is less or gentle slope or less gravity, then it begins to show the deposition morphology. So to make it sophisticated, we can still more apply the deposition parameters or deposition factors added to it. But here we can also show in the free surface flow. So it was rapidly accelerating downslope. And when there is no gravity or the horizontal runout zone, at the time the solid has begun to show the deposition morphology in our simulation also. So we have shown that it can be applied to both the regions.
Yes, Dr. Kattel, because when I read your papers that published in Engineering Geology and Acta Mathematica, and you have shown these, the relationship and the modeling in that papers and some other papers also, and definitely we can do that, but still you need lots of more boundary conditions which should be validated in the field. So I will take one question from Vivek Ponti in Zoom chat box. So asking, can you provide some detail on how the pressure force is calculated in multiphase model? Associated question is that which equation of the state is used, or Is it obtained by solving a pressure position equation for divergence or density condition, or it is something else?
So, in fact, we have not considered here the pressure Poisson equation. So actually, pressure has been included as the local pressure in our equation. So it is purely hydrostatic pressure. But our colleague, Dr. Pokhrel and Dr. Khatri, uh, they have considered in their model, in the mixture flow model, the pressure Poisson equations where pressure rate dependent rheology has also been employed. So as for the flow situation, we can still make the model more sophisticated by incorporating those also. But here we have considered the local pressure in the hydrostatic pressure in the model.
Yes, thanks. I would like to request our participant to put your question within 10 minutes, and then we'll stop taking question after that. So another question from Jeevan Regmi, asking, very interesting. So one to hear the physics of debris flow more on coming days. Could you please explain the few lines on 3D flow? It's a big question, but Dr. Kattel, can you just make thought about how we can use this three-dimensional flow in debris flow in days to come?
In fact, the previous numerical experimental results were geometrically three-dimensional, but they were velocity-wise two-dimensional only. Let's say quasi three-dimensional flow, because to obtain the velocity in the x, y, and z direction, it requires a lot of computational effort, computational complexity. It might take months and months for even the supercomputers to get the results. So for the large scale flow to simulate. So the jet direction has been averaged by the debris flow depth. So we do not calculate the velocity in the jet direction. In fact, the velocity calculation of velocity in the jet direction is also important, but in the modeling approach, it is not possible to get everything and every physics out of it. So we have to compromise. It is a kind of compromise, but still we can add more physics of flows there. So in comparison to the existing other models, then our model has incorporated more physics of flow, but it is geometrically two-dimensional, three-dimensional, and velocity-wise two-dimensional. As we have not computed in the jet direction, but later by relaxing the y direction, we computed the x and z direction. I showed the result of wet snow avalanche obstacle interaction, Khatri et al., where I am also one of the co-authors. There we can show the in z direction also. So we have to compromise either in y direction and the z direction, but x direction is important. We always keep it. I don't know how far I could make it clear.
Now, I mean, this is a fundamental question that the model should always be improved with improvement of different mathematical relationship and the field conditions. And yes, we can discuss more and more, but whatever you explain is quite interesting. And another question from Ishwar Mani Adhikari, a very nice presentation. So asking, does it have any connection to time minimization aspects on such flow for optimization approach?
So I have to say sorry because I have not seen this aspect. We have done some sensitivity analysis on some other parameters also, but we have not carried on this optimization in the time constant. So I'm really interested to say, pardon, Dr. Adhikari, Ishwar Mani Adhikari.
Yes.
Yeah. I think I could contact you and then we can work together if you are related to that field. So I know more about that from you, then we can share the ideas in the days to come.
Dr. Kattel, what Ishwar Mani Adhikari is mentioning, it is really, really important aspects that we have to think when we are working on these flows methods, especially in the Himalayas, where we have a steep terrain and then we have a narrow valley and then flat land, so lots of dynamics. We have to really think on that. So another question from Ramchandra Dungana, asking, which scheme have been considered for simulation?
The scheme is the central differences scheme, and it is especially the total variation diminishing. So if you belong to from the field of mathematics, you understand it. Total variation we have from the function of bounded variation, we have total variation because we give some artificial diffusion in the model, but the model shouldn't diverge. So it should converge. So it is the total variation diminishing so that the model will be effective even if there is large deformation and the shocks are produced. So it is the total variation diminishing non-oscillatory central model. Most of the simulations are performed in that way.
Yeah, question related with this from Pavan Shrestha. Why central differences schemes? Why did you choose that scheme? Why not other?
So central differences scheme that they have been largely effective to address the large deformation and the rapid flow in the gravitational mass flows. So many researchers are using this, so we also employed that.
Thank you, Dr. Kattel. And what I see here in Facebook that Dr. Boral is mentioning that if we can validate that your model in the field, then geologist and mathematician can work together. Of course, I mean that's what we want, and that's why we invited Dr. Kattel to give his talk. And Dr. Boral, thank you very much for this interesting suggestion and comment. We have to work together. So, Dr. Kattel, I have some observation after listening your talk and while discussing with you for a long time and other thing. For example, because when you presented your model about glacial lake outburst plot, so in the end moraine, what we call the terminal moraine, in your model is more tapering from towards the terminal moraine, but generally in the Himalayas, what we see in the Mon moraine, the glacial lake are more widening. So if you change this, the dimension of that glacial lake, what would be the effect in your model? Can you explain a bit? Because we have in this participant list, we have people from different background, mostly from science, but there are other people also who are working on disaster risk reduction who doesn't have that much mathematical background. So can you explain a little bit how can, for example, you can take some Gulf event, for example, or the glacial lake like Tulagi or Chorolpa or Tampukari, or there are lots of in Nepal, Himalaya. So can you explain a little bit shortly?
In fact, as the students of mathematics, we took some regular shapes as the lake. For example, we took the rectangular shape, and then in the third simulation, we have the laterally widening lake also. So we can take this lake in any shape. At the time, we just have to give some geometry out of it. But actually, we didn't have the actual measurement of the lake and the potential geometry of the triggering of the landslide, and then everything we didn't have because we didn't have the close working together with them, except some interactions with you. So we took the simple geometry and then we proceeded, because for mathematics it was sufficient. Then we focused on some modeling approach. But actually we can take the moraine in any shape and any material composition. There we can vary there are so many parameters that I discussed, the different density of the rocks, and then different friction angles of the solid, and then viscosity of the fluid. So there are so many parameters we can vary. But if we get that data of the field or the structure of the moraine, then we can model that in our computational experimental setup, and then we can perform the numerical experiment.
Yeah, that's quite understandable. I mean, if you take the lake as a rectangular shape, it should be the ideal condition. But in the reality, the shape of the lake is quite different, which is not actually in rectangular. But nowadays, it's quite easy. You can take lots of information from Google Earth also. You can see the three-dimensional view of this moraine, and then there are lots of photos that you can validate that model in days to come. So I'll take one last question from our participant in Zoom chat box from Ramchandra Dungana. What are the limitations of your two-phase model? Dr. Kattel.
Yes, it has some assumption that we have made, because we have not incorporated the surface tension, and the upper surface is made the traction free, and bottom surface we have made the no slip condition we have considered, and we have not even considered some air bubbles entrapped during the flow. Sometimes we can see the surfs or the air bubbles, and we have not included there. But that we can include in our three-phase model that is still in the maturing phase, that we have developed the model, but it is yet to be depth integrated, and then we can add some more physics on it. But there are some limitations that there are yet, because sometimes the temperature might have some effect, but we have considered in the isothermal condition. So there are, yes, I admit that there are some more limitations of the model also. So it takes time to make the model more sophisticated and to incorporate more physics and that. Yes.
Yes, definitely. If you use this model, there are always limitations, because you have to set up the boundary condition, and that boundary condition are based on the field based evidences. And this 2020 year is triggered many landslides and debris flow from small scale to large scale, from short distance run out to long distance run out. And the government of Nepal is planning to find the safe settlement area for relocation of those victims in the disaster risk reduction perspective or reconstruction perspective. And on that time, I mean, we need to know, how much, how far the debris flow could go. And that should be understood by the policymakers or the scientists while selecting the sites. So, while I've seen your model, there are lots of, time sequence interval, like 5 seconds, 10 seconds, or 20 seconds. So for example, if we have some settlement down and then we have a debris flow at the top, so can we use your model, based on the field evidences, and can we, disseminate your understanding or the model understanding to the policymaker for the safe area identification in Nepal? Is that possible, Dr. Kattel?
I hope so, because the model gives, as we simulated or as I presented also here, so we can show the dynamics or the evolution, time evolution of the solid phase, fluid phase, and the total debris bulk as a whole. Then we can give, if you can provide us which part or what geometry, what volume or what mass is potentially triggering due to a prolonged rain or some cloud burst. So by the increasing of the pore pressure, then we can estimate the trigger or the release area. Then we can model that release area to the initial mass. Then we can translate the topography. We can, of course, we may take some mean curvature or something like that. So then we can translate the topography. Then we can have the simulation. Then it can give us some ideas. Then how the flow will move downward and how it spreads in the y direction or the lateral direction also. Then if we have to mitigate some or save some settlements downstream, then what kind of obstacles or the active mitigation measures we can install in the flow path, that we can suggest. If we work together and if you can provide some realistic data, what is the potentially triggering, and then what are the topographical, the terrain slope, and then curvature, something like that. Then we can work together.
Yes, wonderful, Dr. Kattel, and I'm very pleased to know that we can use your model. And yes, of course, we have to work together for sustainable risk reduction in the mountains. And that's what we have to work together between the, the applied mathematician like you and other colleague from mathematics background from different universities in Nepal and around the globe with geologists, engineering geologists, civil engineers, and planners and others. And so, one of the best, one of the recommendation or the priorities of the Sendai framework of disaster risk reduction is that we have to do this, evidence-based decision making. So for the evidence-based, we need a scientific understanding. And that's what we have to work. And as we know that every monsoon trigger lots of landslides and debris flow in the Himalayas, and definitely we have to work together. And I'm sure that we'll work together and we'll involve our colleagues, students, and we'll take guidance from our seniors in this field for modeling and others. And models there is always room for improvement in the modeling. That's the one beauty, that's the one beauty of numerical modeling or physical modeling. There's always room to improve, and that can be improved based on these field evidences. And someday, Dr. Kattel, I dream to travel with you in some of our landslides and debris flows areas in the Himalayas to work together. And IHRR probably will be more than happy to collaborate with you. So before I hand over to Suraj Gautam, Dr. Kattel, do you want to say any final words?
Just it's really a nice time for me sharing with a group of diversified people and having your comments, queries. And so I don't know how far I could make you clear, because there are some limitations, because as the basic physics, which I studied long ago, more than 20 years ago, then focused on the pure mathematics, slowly on switching to applied mathematics and choosing the geophysics mass modeling field. Then I don't know much about the geology and engineering term. Then slowly we learned, then got some idea, and then worked on the mathematics field. But yet I have to learn many things from you all people, and it is really a nice time to be together with you. So I again want to thank Dr. Adhikari and Suraj Gautam for this wonderful platform to disseminate my result. Thank you very much once again to all the wonderful participants in this talk.
Thank you, Dr. Kattel, for your wonderful presentation. I always interested to know more about on this field from you, and definitely I will contact you in days to come. And thank our participant both in Zoom and Facebook for your wonderful questions and lively discussions. So thank you once again. And before I hand over to Suraj Gautam, I would like to express happy Vijaya Dasami, and the Tihar and the Chhat. The festival season is coming, and we have to celebrate and stay safe in this time of Corona pandemic, COVID-19. And we hope to see you after this festival season. Thank you once again, Suraj Gautam, for providing me this opportunity to moderate my esteemed colleague, Dr. Parameshwari Kattel, for this evening. Suraj, over to you.
And my wishes to all of you.
Thank you so much. Thank you so much, Dr. Basanta, for the excellent and electric moderation. We'd like to thank Associate Professor Dr. Parameshwari Kattel from Department of Mathematics, the Chandra Multiple Campus, Tribhuvan University, Nepal, for the wonderful presentation on debris flow dynamics and obstacle interactions through multiphase models. The session was purely technical and was really informative. We believe through the use of such models, we'll be able to understand understand the nature and severity of risks, and also aim to prepare better for the potential hazards. So personally, I'm also quite interested and excited on running such models for the risk assessment. We'd be really happy to work and collaborate in the days to come. The Q&A session was also really interesting with a number of quality questions, and we tried our best to address all of them. And in case you have any further queries, you can please feel free to write to us at info@inhrr.org. I would also like to convey my big thanks to all of our organizing team, speaker, session moderator, and our participants for making this session very lively. We'll be sharing the recorded session on our YouTube channel, and the links will be forwarded to the registered email address. We'd also like to request our participants to fill up the feedback survey form and also suggest us some future potential webinar topics. We will try to address them and make it in front of you. So as we'd also like to mention that Institute of Himalayan Risk Reduction will be more than happy to collaborate and organize this kinds of relevant webinar in the days to come. And since this episode is just before the long and grand festive season, we'd like to take this opportunity and on behalf of Institute of Himalayan Risk Reduction, we'd like to share the greetings of Vijayadashami. Vijayadashami, a festival celebrated as the significance of the good over the bad. So maybe this festival would clear all our hurdles and we'll be able to overcome this pandemic situation. However, we'd like to wish you, we'd like to request you to celebrate this Dasai in a safe and isolated way in this COVID-19 situation, because we can celebrate such festive seasons in our future days as well. But for now, being safe and healthy is the most important thing. And thank you so much. And with this, we'd like to sign up from our session for today. Thank you once again. Stay safe. Namaste.
Namaste. Bye-bye.
Namaste. Bye-bye.